Hello everyone, my name is Deepti Mittal. Welcome back to Grade Up. So guys, we were studying about instruction cycle in our CO video lectures. We are studying basic organization of our computer. In these video lecture, we are studying the basic organization of our computer system. We started with instruction cycle. First thing which we studied in our instruction cycle was fetch cycle, and next thing I told you is execution cycle. But for understanding our execution cycle, I told you that we need to study all the instruction formats and then we have to study CPU organization for that particular thing. So in our last video lecture, we just finished CPU organization where we discussed three types of CPU organization. First one was stack CPU, second one accumulator CPU, and third one was general register CPU, which were again further categorized into two parts. So leave that part. We discussed almost 3 to 4 types of instruction formats over there. So now we have completed instruction formats. We will move towards execution cycle, because for execution cycle we needed our instruction format. So let us start with execution sequence and execution cycle, which we are going to study today. So before starting with execution sequence, let us take a quick overview on instruction formats. First of all, I told you we need execution cycle for completing the execution of my instruction. Then the main purpose, what we can say about execution cycle is processing of a currently fetched instruction. See, for instruction cycle, the purpose was execution of instruction. And for that execution, first of all, I need to fetch my cycle. Then I will execute that particular fetched cycle. So purpose of execution cycle is to execute the currently fetched instruction. This is the same thing which I have mentioned in my previous video. But I have taken these all information to give a quick overview of the things. So for fetching or for executing the instruction, I need instruction format. And instruction format, what it tells the overview or overlay which is followed by the instruction, and it was of 5 types on the basis of CPU organization. We discussed 0 address, 1 address, 2 address, 3 address instruction format. So it was of different types. Let us move further. So guys, what can I say about a CPU? There are 2 types of CPU. One is variable length instruction supported CPU and second is fixed length instruction supported CPU. What does that mean? That is, if your CPU is a variable length supported CPU, then it can support variable length instructions. That is, it can support a 8-bit instruction also, a 16-bit instruction, a 32-bit instruction, and so on. That is, it can support instruction with variable length. See, suppose your opcode size is 8-bit and address size is 16-bit. This is also 8-bit. I am really sorry for this. In this case, I have taken it as 8-bit. For one address instruction design, suppose you having one address instruction design means you will have one address in your instruction, opcode and address. So 8-bit, 8-bit. This is 16-bit instruction. In 0 address instruction design, it will be of having only opcode in the instruction. There is no address which is present in your instruction. So it will be a 8-bit instruction. If your CPU is variable length instruction supported CPU, then you can provide instruction of any length, 8-bit, 16-bit according to your requirement. But if your system is a fixed length supported CPU, fixed length instruction supported CPU, then your instructions should be of same size. Then there is a problem which arises. Let us see. In your one address instruction design, you will have a opcode of 8-bit and address of 8-bit supported. But when you have 0 address instruction design, this time you will have only opcode part in your instruction. But if you are going to have only opcode part in your instruction, then your instruction will be of 8-bit. But you are supporting only fixed length instructions. It should be of 16-bit. So this is the problem which arises here. Is in some instruction opcode is of 8-bit, but in some other instructions opcode is of 16-bit. That is, you have to merge your address part into the opcode part. This is the problem with fixed length supported CPU. So how you are going to resolve this problem? This problem will be resolved by using expand opcode technique. What the technique which we are going to use is expand opcode technique. Okay, what this technique is going to do, suppose, see, you are having 8 bit of opcode. So possibilities are 8 zeros to 8 ones. Okay, these are the possibilities for your opcodes. But for zero address instruction design, you need a opcode of 16 bit. So how you are going to design such type of instruction? You will take an opcode, you will borrow a particular opcode from here. Suppose you borrowed 8 ones. Okay, when you are going to have your 8 bits as ones and all other 8 bits will follow the same pattern. Okay, so see, when these 8 bits are going to 1, you can clearly specify that these type of instruction having 16 bit of size, but they are zero address instruction. They will be depicted like that only. But if you are not going to specify this thing, you will depict them as one address instruction, then problem will arise. So for this purpose, what we are going to do, we will take some opcodes from my one address instruction and I will fix them for my zero address instruction. In this manner, expand opcode technique works. Okay, now I think that you are having a basic idea how expand opcode technique works. Let us see. I have taken an example for explaining this expand opcode technique concept to you. Guys, I always say the same thing, that for referring or for teaching or for studying a particular concept, it is always better to take an example, because when you study with the help of example, you remember things for a long time. Plus, it helps you get the concept clear very easily, and it is really good for your practice purpose also. So I'll suggest, while I am solving this question over here, take a paper and pen and solve along with me for better clarity. Let us start. See, consider a hypothetical processor which supports 8 bit of instruction. Here your instruction size is 8 bit with 4 bit of address. Address size is, see, instruction size, first of all I'll write the data which is given to me is 8 bit. Address size is 4 bit. And it is saying if there exists 14 one address instruction, how many zero address instructions are there? So for one address instruction, what is the format? Opcode and address. This whole is of 8 bit and this address is of 4 bit. Then opcode size is also 4 bit. So now tell me, using these 4 bits, how many opcodes are possible for these instructions? 2 raised to the power 4. Total number of opcodes 2 raised to the power 4. Total possibilities for opcodes or total number of operations will be 16. But see, the question is saying if there exists 14 one address instruction, that is we are using only 14 one address instruction. If I am using 14 one address instructions, then 2 of the opcodes are wasted. Or we can say these 2 opcodes are free from getting assigned to any of the instruction. Now I have to find the zero address instruction. For it to be a zero address instruction, my opcode size will be of 8 bit. So if you remember the last example which I took one opcode as 8 ones and used it to make a zero address instruction. But here we are having 2 of such kind of opcodes which are free. So I can use 2 of them. And now it is asking how many zero address instructions are possible. So guys, in these 8 bits, 4 bits and 4 bits. Out of these 4 bits, 2 possibilities are free, and from these 4 bits all are free. So number of possibilities which I can make here is 2 raised to the power 4, and total possibilities will be 2 into 2 raised to the power 4, that is 32. What I mean to say is total number of zero address instruction which are possible is 32. Because to these 4 bit you can assign 2 raised to the power 4 number of opcodes, and by using these two combinations they are 32. I think you get this concept. Now I'll generalize this procedure. I'll give you an algorithm to find out such kind of problems or to solve such kind of problems. See, first of all, what you have to do, you have to identify the higher order instruction format in your CPU. That is, in our last example, the higher order instruction format was one address instruction. Okay, so you have to first identify, then identify the total number of instruction possible in that order. That is total number of instruction which are possible with that order. There it was 1 and total number of instruction was possible was 16, because by using 4 bits I can generate maximum of 16 combinations. Then identify the free opcodes. That is, there we were making 14 opcodes for instruction, and that is we were using 14 opcodes for my instructions and 2 were free. So I have to identify that free number of opcodes. Then calculate the derived instruction set by multiplying the free opcode with the decoded form of address field. See what this line means. Whatever instruction type you want to derive over there zero address instruction, and it will be obtained by multiplying the free opcodes which were 2 over there with decoded form of address field. Their address field was of 4 bits and its decoded form will be 2 raised to the power 4. You know what is decoded form means? Decoded form means all the possibilities. With 4 bits total possibilities are 16. So total number of instruction would be 32. So for calculating expand opcode technique and number of instruction, remember this procedure. It is very simple. Let us now move towards instruction execution sequence. We have studied all the basic things which are required for your instruction execution sequence. Let us actually start with execution cycle. So guys, for this purpose, I have taken an example of my real life. So I will use a real life example which we actually do, and we will study this particular concept. Let us see. Suppose I have taken some assumptions, some type of CPU for calculations. I have assumed CPU as accumulator CPU. That is, I am going to use accumulator CPU, which is also known as 8085 CPU. Instruction format which I am going to use here is one address format. Expression. Suppose I want to calculate A plus B. This is the reason I was telling you that I am using a real life example, because we used to calculate A plus B with the system. Now we will see when we type 2 plus 3 in a calculator, how does it function. We will actually see. Isn't it sound interesting? Sounds interesting? So just be focused. Sorry. Variables are in main memory. It is given that these two variables A and B are stored in the main memory. So guys, I want to calculate A plus B. I have written my program A plus B. You know how to write program. You might be aware of C language. After writing the program, compiler will be going to do some processing. What processing compiler do? Whatever variable you define, it assigns a memory location to it and check for some value over it. Suppose variable A is assigned an memory cell with address 2080 and variable B is assigned a cell with memory address 4060, and these are the values which were stored over there. After this processing, what compiler do? Compiler produces its machine code, and the machine code over here is load A. We will load value of A to my accumulator, because for processing of any expression using accumulator CPU, one of the operands should be present in my accumulator, and then I will add it with B. This is the machine code. So for obtaining this A plus B, I have to explain you two instructions. One more thing, when this machine code is generated, it gets stored somewhere. Yes, it gets stored in memory. Suppose it gets stored starting location with 1000 load, because suppose this memory, we are using 8085 CPU and over there one cell is of 1 byte size. So suppose this load is of 1 byte, then I'll store address using little endian scheme, then this instruction. So in this manner, this program is getting stored. Let us see the actual execution. Okay, guys, now I want to execute my program. So see here. See, I have to explain instruction fetching and instruction decoding. Now I hope that you are clear with instruction fetching. You know how to fetch a particular instruction. We will just recall. I want to execute my program from 1000 and PC will be loaded with 1000. CPU will generate a memory request to read the memory, because you have to read the instruction. This information will be given to system bus. System bus will read the memory, which is load. It is again given to system bus and now it is returned to my CPU. Now CPU has this load. Fetching has been done. PC is now updated to 1001. Okay. When CPU got this load, now it will give it to instruction decoder. CPU has some instruction. CPU want to execute it. For its execution, CPU should know the meaning of this instruction. To know the meaning of this instruction, CPU will give it to instruction decoder. Now decoder. Let us see this functioning of this decoder. This decoder is going to function three things. Whenever an instruction is given to decoder, one instruction can demand 2 or 3 things. First, it can demand a ALU operation, suppose addition, multiplication, subtraction. One, data transfer. Okay. So, this decoder is going to give signal to ALU. If this decoder is going to get any instruction which require any ALU operation, then it will give signal to ALU. If it requires some data transfer operation, it will give signal to system bus. If it requires some internal communication between the CPU, it will give signal to local bus which is connected with my CPU. So these are the 3 signals this particular instruction decoder is going to generate. So this instruction decoder, now check, I have provided with load instruction, and load is of one of type of data transfer instruction. Now it will give signal to system bus. System bus will be activated and it is told that you are required to perform your data transfer operation. One more thing, after getting this load, decoder come to know that it is a one address instruction. So I have to fetch the remaining part. So now this PC 1001, now it will generate a memory request, and in the same manner this 80 and this 20 will be fetched out, and PC is made incremented to 1003. This is 80 and this is 20. You will say that we have bring these two information, these two data to my CPU. Where you are going to store this data? This should be the question which should come to your mind. Yes, CPU is provided with a register file, and for storing these addresses which are part of some instruction, it used WZ register pair, where this 2080 will be stored for further processing. So guys, here we observe 2 things. First of all, instruction fetching, and second thing, all of these things were instruction decode. So you were already aware of the process of instruction fetching. Now you will tell me what will happen in instruction decode. Yes, tell me now. In instruction decode, decoder will give signal to the required hardware, either ALU, system bus, local bus, and the remaining part of the instruction will be fetched out. Now my system is having the complete instruction. Next thing, the process was, after fetching this instruction, I have to execute it. So this instruction is load 2080. That is, I have to transfer the memory content of 2080 to my accumulator. This process is known as operand fetch. Till now, I have completely fetched my information, that is instruction. Now I have to fetch the data actually. Actual data will be fetched out in this operand fetch part. How it is going to do? Your WChat register pair over here is having address 2080. This time CPU is going to generate a memory request for 2080 and which is also a read signal because you have to read the data. It will be given to system bus. System bus will go to memory, and you know what was the memory content of? See, this is FC. This FC will be brought to my data lines, and these data line will return this data to CPU, where CPU will load it to accumulator. Because after all, accumulator is my part of CPU now. CPU will do this process. This is the process of operand fetching. Now this instruction has been completely executed. You have to do what this instruction was demanding. Transferring of memory content of 2080 to my accumulator, and this instruction has been completed. But for execution of statement A plus B, I have to execute two instructions. Let us see what we are going to do in my second instruction. See, for second instruction, my PC was 1003. Again, I will fetch the instruction. I am not going to show the same procedure again. Now you are aware, my CPU now having this add, which is given to decoder. Decoder is going to give signal to three things: local bus, ALU and system bus. Now this decoder come to know that instruction is add. It came to know that it is a one address instruction. So remaining part should has been fetched out. So it will give signal to system bus for fetching of the remaining part. Also it will give signal to ALU because it required to perform some mathematical operation. So it will give two signals. One signal to ALU and one signal to my system bus. In instruction decode phase, one signal is given to ALU and system bus will fetch the address 4060 in WZ register pair, and PC will be incremented to 1006, where next instruction may be stored. Okay guys, this is instruction fetch and instruction decode for I2. Let us see what is the remaining part. Okay guys, see, this instruction was add 4060. So for my addition, first of all, what I need to do? Instruction fetching. Then I decoded, I came to know. Then what the next part which I might have done over here is fetching of after fetching of instruction and decoding of instruction, I should read the data from 4060 because I have to perform the addition. In the same manner, I have done operand fetching for this particular instruction. So three things are same for the above instruction and this one. Instruction fetch, instruction decode and operand fetch. Now come towards next thing. Now I am having A in my accumulator, B in my memory. I want to perform addition. See, in first instruction I need to read my operand from memory because it has to be bring to accumulator. In second instruction I need not to perform operand fetching because ALU in my accumulator CPU can read one of the data item from memory directly. But now it has to perform A plus B. So there is some extra work which is required. This extra work is known as processing of data. You are having input data, instruction. Now you will perform ALU operation over there. That is addition of data on these memory location. Addition has been performed. After addition, you have to store your data somewhere. This is known as write back. That is, whatever result you got, you will store that result back to your accumulator. So what can I say? whenever I have to execute an instruction, there are 5 things. First of all, fetching, decoding, if required operand fetch, if again required and process data, and then write back. So these 2 are the mandatory phase and these 3 depends on my instruction. See, in my first instruction I needed operand fetch, but in my second instruction I needed these 2 phases. So what can I say? If I want to execute a particular instruction, then I may go from these 5 operations, or what can I say, 5 stages. So this is the same thing I have written. For instruction execution, let us summarize what we are going to do. First of all, CPU is going to read the instruction from memory, which is known as instruction fetch. Then this instruction fetched, whatever information you have fetched will be given to decoder, and this instruction, whatever you are fetched, will get stored in my instruction register. That load get stored in my instruction register inside the CPU. It is also a compulsory register which holds the result after fetching and which gives the information to my decoder for its further decoding. During decoding process, what we are going to do, we will fetch the remaining part and we will know whatever operation we have to do, and we will enable the hardware of that particular operation. After that, we will perform, this is operand fetch. This is my mistake. I'm really sorry for that. This is operand fetch. Then after fetching the instruction completely, either you have to perform some mathematical operation or you have to do the operand fetching. That is reading of the data. Then you will read the data. After reading of data, you will process it by enabling the hardware, and then you will store your results back. So there are 5 things basically: instruction fetching, decoding, operand fetching, processing of data, and write back. This is how our instruction is going to be executed. Let us discuss a previous year question on the concept which I have discussed. Guys, I have not discussed a good number of questions in my last videos because I try to limit the time for a particular video, because if I am gonna make it longer, it may seem boring to you or you might not find it interesting, or if you are having some short videos, then you can watch them while walking or traveling somewhere in metro or somewhere else. So I try to make videos smaller, but you don't worry, I am going to discuss a good number of questions on this particular topic in my previous year questions. Also, these topics are the basic building blocks. They are not having so many direct questions on the concept, but all the concepts are required for my further study. So you cannot say that this is not important. Yes, this is important. Let us discuss a previous year question. This question was asked in GATE CS 2016. It is quite a recent question, you can say. See, read the question along with me. A processor has 40 distinct instructions and 24 general purpose registers. A 32-bit instruction word has an opcode, 2 register operands and an immediate operands. Number of bits available for immediate operand field is. Here it is saying that you are having a processor which has 40 distinct instructions, 24 general purpose registers, and it is also given us the size of the instruction. The size of instruction over here is 32-bit, and it is also mentioning the thing which are the part of my instruction. See, opcode, register, 2 register operands, and 1 is immediate field. Immediate operand, you might be confusing with what is an immediate operand. Don't you worry, you just take it as of right now, take it as some other field, like we have taken some memory content. I will explain this during my addressing mode video, so you just don't worry about this thing. So now it is asking, this is whole of 32-bit. It is asking that how many bits are available for this operand. See guys, this opcode tells the number of operations we are going to perform in my system. So here we are going to perform 40 distinct instructions. That means we are going to perform 40 distinct operations. For representing 40 distinct operations, number of bits which we need is log 2 of 40. and that should be a floor value, which is 6. So for opcode, I need 6 bits. 24 general purpose register. For representing 24 general purpose register, maximum bits which I need, log 2 of 24, which is 5. This is also needing 5. So 32, let bit for immediate operand field is x. So 32 is equals to 6 plus 5 plus 5 plus x. Then x will be 16. So what can I say? I am going to have 16 bits which are available for immediate operand field. So answer is 16. Guys, you can see this question was really easy. It was asked for 1 marks. For such type of question, if you are going to lose your marks, then it is a great loss. See one thing, if you are going to lose marks or not going to attempt a question which is really tough, then that is not something for which you should worry, because that is a question everyone is going to leave. Almost everyone is going to leave. But when you lose marks for some question which everyone is going to attempt, then it is a loss. So try not to lose marks in such type of questions. So guys, in this video lecture, we just finished execution cycle. So now we have completed our instruction cycle, fetch cycle and execution cycle. First instruction will be fetched out, executed, then this process will continue. We'll fetch next instruction, then execute it, and then continue and continue. So in this manner, my instruction cycle is getting executed. And how instructions or programs are getting executed. Till now, we came to know about computer functionality of my program, which was program execution, how execution is carried out. So till now guys, I think I have completed all the basic organization or the basic things which are required for computer organization. In my next video lecture, we are going to discuss some question which has been asked in previous year of GATE examination. So guys, till that time, revise all the concept on these topics: CPU organization, memory organization, input-output organization and everything. Then we are going to discuss some questions. Thank you for watching this video. Till that time, practice, because practice is the key for your success. Thank you again.